everybody, it's Norm from Tested, and I'm so excited to introduce you guys to this guy right here. It's Kishore Hari. He's the director of the Bay Area Science Festival. Now, I'm not interviewing Kishore because we're going to be interviewing some people together.
We have an amazing lineup of people we're talking to about robots.
Robots, bio-robots. Now, we're here at the Swiss Next Institute. They bring organizations and researchers from Switzerland, and tonight we're speaking to people from the EPFL.
EPFL, one of the major science institutes in Switzerland, and we have a special biomimicry robotics group that came over that model all sorts of behavior of snakes and fish and salamanders and reptiles, all to understand how biology from nature can really inspire the next generation of robotics.
Bio-robots, lovable or creepy? Let's find out.
Hi, I'm here with Auke Ispiert, and to talk about these wonderful biomimicry robots you have. Who do we have on display here?
So this is Amphibot. It's an eel-like or lamprey-like robot.
So remind us, what is a lamprey versus an eel?
Yeah, so lamprey is a very primitive vertebrate. It's one of the oldest vertebrates existing, so it's still a fish. Eel is a bit more advanced. Both are fishes, but they both share exactly the same type of swimming.
It's that basic sort of undulation through the water?
Absolutely. It's called anguilliform. You have a nice traveling wave undulation propagated from head to tail.
And why did you want to study a lamprey motion? You said it's one of the most ancient animals. What can we learn from something like that?
Yeah, there are two main purposes. The first one is for neuroscience. It's like a tool for neuroscience to understand the spinal cord of the real lamprey, because it's probably the animal of which we know best the spinal cord. So we use it as a test bed, basically, to test hypotheses of how it's organized.
Meaning that a lot of neuroscientists have been studying that lamprey for a long time, especially the spinal column?
Absolutely.
Does it have like a brain, like how we associate brains in other animals, or is a lot of this controlled through the spinal column?
Well, that's the interesting part. It has, like any vertebrate, the upper part of the brain, and it has a spinal cord. But for locomotion, it's really the spinal cord which is a key element. And people know it, like you can cut the head of a chicken, can still run for a while, because the spinal cord is really the controller for locomotion.
And even though it's simple motion, how complex of a creation is this robot?
Well, the big challenge was to make it waterproof. There we suffered a bit. So we had some generation to make it really waterproof. Otherwise, what's nice, it's a very modular design. So we have little elements. Every module has its own microcontroller, battery, and it has a CAN bus to connect them. So we can very easily make the robot longer, shorter, or even add legs. Later on, we'll see a salamander version of this robot.
And how long are lampreys usually?
So lamprey, an adult is like 1 meter.
1 meter.
1 yard, yeah.
And when you are testing this robot, are you looking at that specific 1 meter length, or are you looking at even longer lengths or even shorter lengths to model this kind of estimated pattern?
For us, because as you'll see, we have some kind of granularity problem, like the fact that the modules cannot be too small. It's good to be at least 1 meter. Otherwise, you cannot really propagate properly the traveling wave.
And how long can this thing go in the water?
How long it can swim?
Yeah,
probably for half an hour non-stop easily. Possibly, if you have a few stops, for 1 or 2 hours.
And so, tell us about the intelligence in this. Like, it's one thing for this to swim through. We've all seen those toys that swim through the water that are just going through the same motion. What are we seeing inside here in terms of the intelligence?
Yeah, the intelligence is really this kind of replica of the spinal cord circuits. And what's nice, it's a very distributed system. So you can almost cut it in half, and subparts of the spinal cord can still work. And not the animal, though. The animal would die. It's not like an invertebrate, like a leech, but the lamprey would die. But you can really, it's a very distributed controller, let's say. And what's interesting, it's very robust. So you can really modulate it, disturb it a lot. And what's maybe the most fascinating is the signals coming from the upper part of the brain being sent to the spinal cord are very simple. Just 2 signals. You increase both of them, you go faster, you stimulate more one side, and you'll turn towards that side. So you see a demo when it swims, it's very easy. It's as if you had a remote control car, like just 2 signals to control the whole locomotion. And I think that's nice, because that means the upper part of the brain doesn't need to worry about muscles, what every muscle should do. It's really the job of the spinal cord to do that. And an upper part of the brain will just do high-level modulation.
And so this controller basically has what you said, just those 2 degrees of motion.
Absolutely. So Alessandro Crespi here, the postdoc in the lab who developed the electronics of the robot, is basically playing the part of the upper brain, let's say. And then he sends these very simple signals to the spinal cord model, and that's running in real time now with little mathematical models on board of the robot.
How complicated a mathematical model is it to mimic this behavior?
It's fairly simple. Like the complexity comes from coupling the oscillators together. So it's a network of coupled oscillators from a mathematical point of view.
What does a next generation of this look like?
So we have a new version which is longer, more rugged like for field, like a field robot. So we use it for pollution detection. So we have a GPS on board. We can do navigation.
So it'd be autonomous. It can
Absolutely.
we can unleash a number of these throughout a water system.
Yeah, you can give waypoints. It will go to the waypoints. Or more interestingly, it should be able to find the gradient, like climbing where the pollution comes from.
And even that sensing equipment, I mean, we've seen GPS get that small, but the actual chemical detection can be miniaturized into something this small.
Yeah, that we have colleagues in Lausanne that work exactly on that. So that's not our job, it's their job. But they do a very good job for some of the sensors to have them on board, absolutely.
Oh, this is a cute little guy.
Yeah.
I have a little fondness for him. Do you have a fondness for the animals?
Yeah, absolutely. You know what? This is one of still my favorite robots that we have in the lab. And one of the reasons is that if you take it out, the appearance looks like nothing. It's just a set of boxes connected together. But what makes it cool is the motion. It's the motion that makes it lifelike. So easily we could make a skin over it to improve the appearance. But I like this notion that the appearance is not so beautiful, but the motion is beautiful.
Thank you for showing us the lamprey.
You're most welcome.
And so from water-based systems, we move to land-based systems, where locomotion is a little bit different, but snakes, we have land. So this is Camilo, and tell us about your snakes.
Okay, well, these snakes are a robot that are very simple, let's say, in the way they're constructed. For example, we have one motor that have only 1 degree of freedom. Then we just twist the motor to have another degree of freedom like this, and then we just continue with the same chain, doing all over the number of models that you want to put.
Now, in terms of biomimicry, you're trying to mimic the versatility and the motion of a snake. A snake doesn't actually have just 1 degree in turn, or does it?
No, it doesn't. I mean, depend on what gait you will try to reproduce. For example, you can see that actually the body moves like a real snake, right?
Yes.
And we have also this vertical plane, so you can move it in many directions. So depending on the gait you're trying to do, for example, side-winding snakes, you can just reproduce it the same way as the real snake does.
When you study a land snake, right?
Yeah.
And its gaits, it can slither forward, like you say, it can move sideways, it can coil. Which are the motions that you find most interesting for this type of robot?
Yeah, there is one motion that is quite interesting, is this one. You can see, this is called rolling. So basically what we are doing is just try to maintain this arc shape all the time, but the robots are moving all the time like this. So every model just move like this, but as you can see, you combine this motion and you have a rolling. So that's very interesting because, for example, you can wrap around something like a pole, like a tree branch, for example, and then you just roll and you can just progress with this motion.
So it's how it's traversing along other long objects, basically.
Correct.
Some type of a pole or a girder.
Or even the ground.
Or on
And
the
also
ground
you can
even.
have a little bump, but you can still pass over it.
Right. And so when you're designing something like this, it's not just to illustrate how you can use engineering mechanics to mimic the biology of an animal, but there's also practical application.
Yeah.
It's not just making robot snakes for robot snakes that tie around Kishore's neck.
It is. But the practical application that we most envision is, for example, going to a search and rescue mission, right? So, we have this cross-sectional. So basically, this is super slim, so you can put it through any borehole that you can imagine, like this size. And then you can just, once inside, you can just move and do a lot of things, right? So as I mentioned, we can have different types of gates, so it doesn't matter how the terrain is, how it looks. You can still try to go in this gate and then just change to another one. So this is what we call multimodal locomotion. So this is pretty, let's say, convenient for this kind of scenarios.
And imagine putting a camera on a robot like this, very useful for search and rescue. Now, how does this scale? Can you add more links to it and make it a longer snake? Does that change how it moves?
Yeah, of course. For example, I'm going to show you something. We have here 8 degree of freedom. That means 8 modules. It's quite a small snake, but still we can do a lot of things. This big one over here, it has 14. This one is 16. And this one here has 24.
24. Wow.
So you can see that we can scale. The only, let's say, drawback is that as you scale the size, you need more battery power.
Yes.
So in that case, you need to put, for example, in the head, we have this controller in one end, and in the other one we have the battery. So if you scale it even more, you need a large room, let's say, for the battery.
But the software also scales
Software
appropriately.
is exactly the same.
It doesn't get more complicated. It doesn't
Not at all.
tie itself
It's
up.
quite simple because basically you just control two waves, one vertical and one horizontal wave, and that's it.
That's amazing.
Yep.
Well, the snakes don't have legs, but we're going to take a look at robots that do. But thank you so much for sharing with us the snake robots.
You want to hold it?
Absolutely. Woo!
From snakes to mammals.
Oh yeah.
What do we have here?
So this is a little cheetah cup. It's a bio-inspired robot modeled after the animal, a cat or a dog. So quadrupedal mammal, terrestrial mammal. The cool thing about this robot are actually its legs. So you have here these three segments, 1, 2, 3,
And this string kind of
with the
connected.
string connected, exactly. So one motor that's sitting here, that's doing the front and back movement, and one motor that is compressing the leg. So for that I have to hold it here a little bit, like compressing here the leg, and the spring is extending.
How much is that like how our arm moves?
Actually quite similar, because you have this antagonistic motion, so you have always one muscle that is contracting and one muscle that is protracting, and exactly that's what the motor does. The motor is contracting and the spring is retracting again.
This seems like a very robust system. How fast can a creature like this move?
Oh.
With what is like